Let's say that you're moving at 110 kilometers per hour. That's 30 meters of road, disappearing every single second. Suddenly, there it is, a massive obstacle right in your path.
Freeze. What do you do in this exact moment?
Naturally, your instinct is to hit the brakes, but will that be enough? This is where sight distance comes in. It is the length of the roadway ahead that is visible to you. Look at the gap. Do you think your distance is safe enough to avoid that tree? This is the first and most critical tight, stopping sight distance. It is the bare minimum distance required for a driver to see an object and stop safely without a collision. And it applies to every single road and street ever built. Your stop is divided into two parts, the reaction distance and the braking distance. First, reaction distance. The distance traversed by the vehicle from the instant the driver sights an object necessitating a stop to the instant the brakes are applying. Reaction distance can be calculated by multiplying the speed of the vehicle and the reaction time. Reaction time is the gap between seeing a hazard and hitting the brakes. Engineers call this the PIEV process: perception, intellection, emotion, and volition. It's the 2.5 seconds your brain needs to analyze the threat and finally act. Second, braking distance. The distance needed to stop the vehicle from the instant brake application begins. Let's put our theory to the test.
Okay.
We need to find the minimum stopping sight distance for a car doing 110 kph on a minus 3.5% grade. We'll use the metric formula. Remember, SSD is the sum of reaction distance and braking distance. First, the reaction distance. In the 2.5 seconds it takes the driver to react, the car travels 76.38 meters. Next, the braking distance. We have the formula V squared over to G multiplied by FG. Since we are going downhill, the grade is negative. This adds physics-based resistance, requiring 194.229 meters to stop. Add them together, and we get a total SSD of 270.609 meters. That is the bare minimum visibility required for safety. Now, here is a professional shortcut. While the physics remains the same, your textbook provides derived equations for faster design. In the metric system, the constants are already baked in. You just need your speed in kilometers per hour and your deceleration rate m per second squared. These derived equations are your primary tools for evaluating the suitability of available sight distances in real-world projects. Now that you've seen how the pros do it, let's put your skills to the test. Okay. Try to solve this next problem to practice your knowledge in stopping sight distance. Pause the video here, grab your calculator, and see if you can find the SSD. Sometimes, just stopping isn't enough. You have to make a choice and be fast. The second type of sight distance. This is decision sight distance. It's the length needed to detect info, recognize a threat, and select a path in a cluttered environment. We provide this extra room at critical spots like ramps, toll plazas, and massive intersections. Because when the road gets complicated, you need time to decide before you act. Let's solve a real-world DSD problem, computing the distance needed to stop a vehicle on a rural road at 50 kph. For decision sight distance, we use two different sets of formulas depending on the driver's goal. If the driver must come to a full stop, we will use the maneuvers A and B that includes braking distance. But for maneuvers C, D, and E where the driver just needs to change speed or path, the formula simplifies to just pre-maneuver and maneuver time. All these values are standardized in Table 3-3, giving us the exact distance needed for every environment. Now let's go back to the problem. For a rural stop, we use Avoidance Maneuver A. Our pre-maneuver time for this is exactly 3.0 seconds. This is the formula for AASHTO using metric system. First, the pre-maneuver distance at 50 kilometers per hour. You travel 41.7 meters just while recognizing the situation. Next, we add the braking distance using our deceleration rate of 5 meters per second squared. The answer is 19.5 meters. Solving for the AASHTO, we will add the two distances. The result is 61.2 meters. If we check our design table, this fits safely within the standard 70-meter AASHTO for this speed. Okay, try to solve this next problem to practice your knowledge in decision sight distance. Pause the video here, grab your calculator, and see if you can find the AASHTO. Finally, we have the most complex maneuver on the road, the passing sight distance. It is the distance needed to safely complete a passing maneuver before meeting an opposing vehicle. Every safe pass is built on four distinct phases. First, D1, the initial maneuver. This is the distance you travel while perceiving the gap and accelerating to the point of crossing the center line. Second, D2, the occupation distance. This is the danger zone, the total distance you cover, all in the left lane. Third, D3, the clearance length. This is your safety cushion between you and the oncoming vehicle. Finally, D4, the oncoming vehicle distance. While you were passing, that red car was racing toward you. We estimate D4 as 2/3 of your passing distance. Add them all up, and that is your total passing sight distance. Let's calculate a real-world pass. Our passing vehicle is doing 96 kph with an initial maneuver time of 4.3 seconds. Let's write first the given and its conversion. First, we solve for D1 using our speed difference and acceleration rate. That will give us a value of D1 that is equal to 122.24 meters. Then, we find D2, the massive distance covered while occupying that left lane for 10.4 seconds. This is equivalent to 277.337 meters. We estimate D4 as 2/3 of that distance to account for the oncoming vehicle's travel, which is equal to 184.891 meters. Add them all together with our 76-meter clearance, and we have our total passing sight distance, which is 660.468 meters. We've covered the math of survival from the bare minimum of stopping sight distance to the complex choices of decision and passing sight distance. Master these formulas, Double-check your conversions and always design with purpose. Our work ensures that everyone gets home safely. Thank you. See you again.